Hello everyone. In the last class, we had seen some general aspects of geophysics, geophysical exploration methods, and we had also had a preview of the important methods that we are going to discuss during this course. Today, we will take up the first major methods, which are known as electrical methods. That is what we are going to see in the next couple of lectures. As I had told you previously, electrical methods are classified into number of sub-methods. The important three methods coming under the electrical group is first is the resistivity method, then the second is the induced polarization method, third is self-potential method, which means the electrical methods are further subdivided into number of methods. Out of them, the most important ones we are seeing today, that is resistivity method, induced polarization method, and self-potential method. Right. Let us have a look into what they refer to. First is the electrical resistivity method. So, electrical resistivity method is based on the variation in the electrical resistance of the formation, right? That means we try to understand about the subsurface of the earth based on the fact that each and every region has got different electrical resistance. That is what is known as electrical resistivity method. The second method is based on measuring the natural potential that are present in the subsurface. This method is known as electrical self-potential method. Here we make the measurement of naturally present potential. Third one is induced polarization method. In this method, we apply some current. The effect of that is measured after we switch off the application of current. Right? These are the three methods which we are going to see in the next few lectures. Let us take up the first one, which is the electrical resistivity method. Electrical resistivity method is an active method which is very often used to understand about the subsurface, especially for geotechnical investigations, to understand the depth to the basement rock in a weathered rock region, also in locating groundwater wells, right? Because this method is being commonly used for different applications, there are also standards brought out by the Bureau of Indian Standards. You can see a code which is 93020 is a code number which highlights how the survey has to be carried out in the field. That means geological exploration by geophysical method, that is electrical resistivity. Code of practice is already available. Similarly, ASTM, American Society of Testing of Materials, also has come out with a code, standard code or guideline for carrying out electrical resistivity method. What is the principle, right? In electrical resistivity method, we are going to apply current into the earth and the potential developed is going to be measured. That is why this method is called as active method. We had seen previously what is active and what is passive. In active method, we are going to generate some signals and the effect of that signal is going to be studied by us. So it is an active method. In passive method, we are not going to generate any signals or create any signals, but we are going to measure the naturally present signals in the earth. Example is gravity. Okay, that is a passive method. We had seen about active and passive method already. Here we are going to apply some current. The effect of that is going to be measured. That means what we are going to do? We are going to measure the potential the measured potential is controlled by some factors of the subsurface of the earth. Here, since we are talking about resistivity, let us take an example of presence of water below the surface. Imagine just beneath the ground surface, the formation is completely saturated. That means it is completely wet, right? That means water table is almost near the surface of the earth. In such a case, here the most important factor that is going to control the measured potential is the level of saturation. So, by carrying out electrical resistivity survey, we are able to understand the level of saturation, which means we are going to measure the factors that affect the potential, right? We are going to understand the factors that is going to affect the potential that we are going to measure. Right. This method is carried out mainly to understand the vertical variation below the surface of the earth. So here this is the ground surface, how vertically the formations are changing below the ground surface. This is ground surface. Just below the ground surface, how the formations are changing. For this resistivity survey can be carried out. Another application, right, I am drawing it on the left hand side. This is the surface of the earth, right. Our interest may be along this direction how the subsurface changes. So here is the lithological contact, here is the contact, here we had sand, here we had some clay, again sand. So this is how we try to understand the variation in the lateral direction. That is what I mean, both in vertical as well as in horizontal direction. What are the changes in the electrical properties of the subsurface? Using that can we mark the lithological contacts. So this is in brief about the electrical resistivity method. Now let us go and understand this method with some more fundamentals, right? What exactly is resistivity? We know very well, right? Ohm's law states V by I is equivalent, V by R is equivalent to I, right? Or in other words, R is equal to V by I, right? This is what is Ohm's law. And here the term R is resistance. The letter R refers to resistance. V is the voltage. I is the electric current, right? What exactly we mean by resistance and resistivity? On the previous slide, we have seen Ohm's law, right? Ohm's law states R is equal to V by I. We have written already. So R is the resistance, V is the voltage, I is the current. So here we have used the term or letter R, which refers to resistance. Then what is resistivity? So resistance is relevant only to a measured circuit. That means the word resistance refers to only to a particular circuit, which means the unit is ohms. That means we didn't bring in the fact of the volume of the material for which we measured the resistance. So resistance, however, will change if the geometry, size and volume of the material changes, right? So that is what I have stated here. Resistance will change if the geometry and volume of the material changes. Hence, it is not a physical property. Therefore, it is not a physical property. That means resistance, the word resistance is applicable to a particular circuit. Okay. Then what is resistivity? Whereas resistivity becomes the property of the medium, right? So it is a property of the medium, hence we bring in the unit of ohm meters. Whereas for resistance, the unit is only ohms. Resistivity is ohm meter. What exactly we mean by resistivity? We said resistance is applicable to a particular electrical circuit for a particular material. However, we need the area as well as length to come out with resistivity. So, normally we take a unit cube. Resistivity is defined as the voltage measured across a unit cube, as you can see in this picture. The resistivity is defined as a voltage measured across a unit cube's length, right? Divided by the current flowing through the unit's cross-sectional area, which means we are referring to amps per meter square. So here is the elemental cube. If the current is passed through this, the current flows through this elemental cube. To determine resistivity, we need to know the size and shape of this material. So here we are talking about a 1 square meter area, right? 1 meter by 1 meter. The length of this cube is also 1 meter. So we can come out with an answer of ohm meter, right? That is what is the resistivity. So resistivity is dependent on the area of cross section as well as the length of that particular object. In other words, we need to know resistance per unit volume is known as resistivity, which is often referred by the letter rho, Greek symbol rho. Rho is often used to represent resistivity. So now we have understood the difference between resistance and resistivity. Resistance is relevant to a particular object for which we don't know its size and shape, which means resistance is applicable only to that electrical circuit or only to that only to that material. Whereas resistivity refers to intrinsic property of the medium or the material. Hence, previously for resistance the unit is ohms, whereas for resistivity ohm meter. The term meter indicates that we have now defined the geometry and size, or in other words volume of the material for which we are going to measure the resistivity. Usually we determine resistance per unit volume. Unit volume is 1 by 1 by 1 meter as shown in this figure. So resistivity, the unit is ohm meter. We have to take into consideration of the area as well as the length. So area divided by length, it becomes ohm meter. Okay, so this is what is the difference between resistance and resistivity. And if one is known, the other one can be calculated as per the relation given here, where resistance is equivalent to resistivity multiplied by length divided by area is the relation that relates resistance with resistivity. So resistivity of the medium can be estimated using this relation by simply rearranging this equation. As you see here, resistivity is equivalent to resistance multiplied by area divided by L, that is the length, right? So if resistance is known, we can determine resistivity. To determine resistivity, what is essential? We need to know the dimension, that is the area, as well as the length should be known, right? Only then we will be able to change the resistance to resistivity. Why we are spending sufficient time on this, right? As I had told you previously, resistivity is referred by the letter rho and the unit is ohm meters. The resistivity is directly related to conductivity, right? What is the relation? They are inversely related. So conductivity is inversely related to resistivity. We have understood what is resistance, what is resistivity. Now we have also understood what is conductivity. So conductivity is 1 by resistivity is conductivity. So resistivity of a material is defined as resistance in ohms between opposite phases. Usually we consider elemental cube. Resistivity is inversely proportional to conductivity, right? So we have seen what is resistance, what is resistivity. Now here we have understood what is electrical conductivity. After having seen these three, I would like to introduce another term known as apparent resistivity. Until now, we have seen the word resistivity, which is actually referring to the true resistivity of the cube, right? We had seen in this page, we have seen a elemental cube. Since we have a cube in our hand, cube of material in our hand, we are able to determine its actual resistivity. Okay, so the resistivity we have determined is known as actual resistivity or the true resistivity. However, when we want to attempt to understand or to measure the resistivity of the subsurface of the earth, that is what we are going to do, isn't it, in exploration, right? Or in to understand the subsurface, we are going to deploy this method on the surface of the earth. Whereas resistivity of the subsurface we cannot measure. Why? Directly we cannot measure, because to measure the resistivity of the subsurface we need to know the dimension, area and the length, right? So we have seen just now we need to know what is the cross sectional area through which the current is passed. It comes out on the opposite side. What is the length of that particular object? So is necessary. That means we need to know the area as well as the length. But in the case of earth, we are going to apply the current on the surface of the earth, due to which we don't have the definite geometry and volume. That is why the resistivity which we measure for the subsurface of the earth is known as apparent resistivity. So apparent resistivity is the one which we measure for the subsurface. Why? Because beneath the surface of the earth, the formation is anisotropic. That means properties are not the same everywhere, and the subsurface of the earth may consist many number of layers of different materials. So we are unable to measure the true resistivity in the field, right? What we measure is only apparent resistivity. So apparent resistivity is estimated based on the way in which we are going to make the measurement on the surface. That means how are we going to arrange our electrodes to make the measurement. We will understand it much more detailed when during the progress of this lecture. And here let us also see how the subsurface of the earth control the resistivity. Different medium that are present below the surface, they are of different character. Accordingly, they conduct the current. Okay. So, if you look at these materials, right, the materials which I have written here, for example, quartz or massive rock, which we use for building purpose. For concrete aggregate, we use a rock quarried from the major quarries that consists of granites or gneissic rock, which are massive rocks. Then gravels. These materials are highly resistant. They offer high resistance to the flow of current. So they are of high resistivity material. On the other hand, low resistivities are ores of sulfates, clays, right? Also weathered and decomposed rocks. Formations that are saturated with water, right? Water saturated formation. Metal deposits, ores of metals. They are all good conductors. So they offer very low resistivity. So resistivity of such formations are low. Why we are looking into these two here? Apparent resistivity of the subsurface depend very much on the material that are present below the surface. Some of them may be offering high resistivity, as you see here, may be massive rocks. Resistivity is very high. On the other hand, at some places we may have low resistivity material, such as common example is clay. Wherever you have clay, current is able to pass very easily. Resistance offered by clay is very less. Right. Let us see little more in detail about apparent resistivity. Why we are unable to measure true resistivity? True resistivity is measured in the laboratory for a elemental cube, as I have drawn here. Only for this we can determine the true resistivity, because we know the area and we know the length. Since we know the volume through which current is passing, we were able to determine the resistivity. Right? Whereas in the subsurface of the earth, even if the material is homogeneous, the current flows something like this, right? We apply current from these two places, current passes into the earth like this, right? When the current is passing through the subsurface, as you see here, the subsurface offers some resistance to the flow of current, right? Due to which the potential gets developed, as you see here, perpendicular to the directions of flow of current. But nevertheless, we are unable to understand the volume through which the current is passing, isn't it? Whereas in the laboratory experiment, we had a small elemental cube with us, so we applied current from one side, other side the current was flowing out. Since we know the volume, we were able to determine the resistivity. Whereas for this case, we cannot understand the volume, though the material is homogeneous. Let us take a much more complex case, heterogeneous medium. That means this is the surface of the earth, right? This is the surface. Beneath the surface, you have one layer. This is layer 1. This is layer 2. Both of them are having different resistivity. So due to which the current will try to fall or follow the zones where the resistivity is very less. For example, in this case, resistivity of layer 2 is less than the layer 1. That means this layer has got comparatively lower resistivity. So what will happen? The current will tend to, most of the current which we apply will tend to follow or flow through the second layer. This is another complexity. In both the cases, whether homogeneous or heterogeneous, we are unable to measure the true resistivity of the formation. So the resistivity which we measure is only referred as apparent resistivity. Hope it is clear to you now, right? We had initially seen what is resistivity, then we had seen what is apparent resistivity. So when we measure the resistivity of the subsurface using the techniques which we are going to learn soon, what we are measuring is only apparent resistivity, right? But the apparent resistivity which we measure is dependent on several factors which are indicated here. For example, first let us have a look into porosity. Porosity control the resistivity or the apparent resistivity of the formation. How? Suppose if the formation has got high amount of porosity, here in this picture you can see the blue zones are pores. If the pores are nothing but voids, you have some mineral grains. Between the mineral grain there are some voids. If the voids are filled with air, the resistivity will be more, right? On the other hand, if the pores are filled with water, resistivity will be less. Thus, porosity is one of the important factor that control the resistivity. Further, whether the pores are connected. When the pores are connected, what happens? If there is fluid will flow and occupy almost all the pores, at least partly. When the fluid occupies part of the pores, resistivity goes down. So, we are able to understand by making the measurement of resistivity or apparent resistivity, we can understand about the porosity of the subsurface formations. Suppose the pores are due to fractures. That means you have a massive rock below the surface of the earth, but the rocks has got one major fracture like this. This is a fracture, right? So, when the fracture is there, the resistivity will be slightly reduced. Why? As soon as the fracture is there in the rock, the fracture will be normally, it is expected to contain or retain some moisture, right? So, resistivity will be slightly reduced. So, the measured resistivity help us to understand whether the rocks are fractured, whether the rocks has got lot of pores or porosity, whether the pores are filled with some fluid. We can understand. That is what I have written in the second statement, right? How much of pores are filled with air, water or gas? Right, especially in oil exploration toward the fag end of this um, course, especially in logging, in well logging, in the borehole, we are able to understand how the porosity or resistivity varied within the same formation. That help us to also understand what is the porosity of the formation. Out of the porosity, how much of it is filled with air, how much of it is filled with water, how much of it is filled with oil can be understood. So, what is porosity? Porosity is the ratio of volume of voids to the total volume. Okay, suppose if I take a elemental cube, right, let us assume it is 1 meter cube, volume is 1 meter cube. So, total volume is 1 meter cube. Out of this, volume of voids is 0.2 meter cube. Then porosity is 0.2 divided by 1. Porosity of this is only now 0.2. That is what is porosity, right? Which means this material can hold only 0.2 cubic meters of water. Whether the entire pores are filled with water or gas or oil can also be determined by resistivity logging methods. So, we can understand which is the zone that is holding large amount of oil can be determined using resistivity methods. Then resistivity is also dependent on the quality of water. Imagine here is a formation, it's a limestone rock which is capable of developing large number of caves because limestone can be easily dissolved by the rainwater, lot of caves gets developed. Suppose if the water is fresh water, right, reasonably good water, resistivity will be little bit higher, right? If the same fresh water becomes saline, rich in salts, dissolved salts, especially sodium and chloride, resistivity will go down. So, water salinity or TDS, that is the total dissolved solids. total dissolved solids, if it is more in the subsurface groundwater, then the resistivity will be less. So this is one of the factors that affect the measured resistivity. Then clay. How clay play an important role? Clay formation has the highest porosity, right? The porosity can vary between 40 to even 55%, which means if you have the same elemental cube made of clay, right, this box of 1 cubic meter, if you fill it with clay, how much of water we can add? We can nearly add 0.5 meter cube of water into this box now. Why? Because porosity of clay is nearly 50%. Due to which we will be able to distinguish clays from the other formations. Why? If the clay is there, it is expected to have retained moisture. Due to this reason, clay formations will give low resistivity. Okay, so clay is another important factor that control the resistivity. Then the next is metallic minerals, especially metals of sulfates, right? Iron sulfate. These metals offer low resistance. Okay, why? Because we all know metals are good conductors. That is why at our homes or everywhere we use metal wires, especially copper or aluminum. They are good conductors. So, ores of metals offer high conductance, so resistivity will be less. And hope you can recollect the example we had seen in the previous lecture on rising magma, right? So, the temperature also control the resistivity. As the temperature increases, resistivity of that formation will rise. That is why we were able to detect whether rocks are melting, right? I showed you an example, right? Then lastly, the rock matrix itself, the small matrix here is a formation. This matrix itself will offer some resistance, isn't it? That is why we have seen metals offer low resistance. Here you have a quartz sand. Quartz is very resistant, highly resistive. So intrinsic materials resistivity also control the measured resistivity. So all these factors influence the resistivity which we are going to measure. Here you can see a picture brought out by this people, right? Here you can see two textures, sandstone. It is a sandstone. Sandstone is a rock where sand is binded by a cementing medium. Here are the two types of sands. Here in this sand, large sands are binded by a cementing matrix. Here, the large grains of sand is binded by a cementing matrix, but the cementing medium also has got some tiny sands. So, both of them will offer different resistivity. This is number 1, this is number 2. Both will offer different resistivity. Here is a limestone rock. Limestone rock has got some cavities through which water is present, water is flowing. The movement of water leads to dissolution of limestone. So the quantum of dissolution or presence of fractures control the resistivity here. Right? In this case, you have sandstone, but sandstone also has got some clay in it. So resistivity will be less. The next one is a rock, a granitic rock. But the granitic rock has got lot of fractures. Fractures are nothing but some joint, some opening in the rocks, some cracks in the rocks. Usually when cracks are there, cracks will have little bit of moisture, due to which when the rocks has got fractures, resistivity will be less. That means in comparison, a fresh rock, no fractures, will offer higher resistivity. The same rock, when it has some fractures, resistivity will get reduced. Here is the last one is the showing the basaltic rocks. Basaltic rocks are found mostly in western part of India, western central part of India, especially Maharashtra, where we have Deccan basalts. So basalt rocks has got a unique property that it will have some voids. How basaltic rocks are formed? Basaltic rocks are formed due to the eruption of magma. The molten rocks erupts and due to volcanic eruption, then cooling of the rock, cooling of lava leads to formation of basaltic rocks. During this process, there are some vesicles formed in the basaltic rocks due to the escaping gases, right? This is the volcano flows, but the topmost layer of volcanic layer or lava flow may try to cool down, become a solid, but the lower layer is still in the liquid form, so lot of gases emanates, they try to escape, right? This gas, escaping gas, forms some vesicles. So pores are present as the rocks getting formed. So basaltic rocks offer a different kind of resistivity. The resistivity measured in basaltic rock depend on the amount of vesicles present or cavities present, whether these vesicles or pores are filled with water or some secondary material. So all these factors control the resistivity of the rocks. So in this lecture, we have seen what is electrical methods, what are the three important electrical methods, then we had a look into resistivity methods. Thank you.